Hi, student. We'll continue on the lecture for bioreactor engineering. Okay, this is the subject that we continue. We're still on the lecture number 4. Number 4 is continue on homogeneous reaction. Okay, which is chapter number 8. For this chapter, we continue on the basic theory of reaction, and then we calculate the reaction rate from the experimental data. So sometimes in the application we use experimental data. Reaction kinetic for biological system, and then we determine enzyme kinetic, okay, using batch data. For example, deactivation yield in cell culture, cell growth kinetic, and is a plasmid. What is a plasmid? Plasmid is some small fraction of what is a small molecule, okay, can be replicated like this. So this is bacteria DNA, and then is contain some plasmid, and then it's duplicate something like that. That is called plasmid. And then we production kinetic, and finally we will discuss about kinetic of the cell death inside the cell culture. And this is how reaction so have two fundamental is about thermodynamics and chemical kinetics. Chemical reaction thermodynamic is concerned with how far the reaction can be proceed, it can be occur or not. And if you talk about the kinetic is how fast of that reaction is, okay, it cannot beyond the equilibrium. This is how the reaction equation look like. A plus B transform into the product like Z and Y, for example. This is equilibrium like this. This is concentration of the product divided by concentration of the reactant, for example. Okay, this is kinetic constant look like. And this is for thermodynamics. At the equilibrium, natural log of constant is equal to delta G reaction over RT, okay, and this is the delta G look like product minus reactant, and this is one of correlation between delta G, delta H, and delta entropy. This is from thermodynamics, and then you change this one to RT. It's the same equation like this. Okay, we might use this equation later on. Okay, we have the example of this one. The isomerization just change some molecule, so it's the same molecular but different configuration. Glucose is isomerase is using in the production of high fructose corn syrup. High fructose, so it's something that is sweet. Delta H enthalpy is this one. Delta S is this one. Calculate equilibrium constant. This one. So you have this kind of correlation. And at this temperature, okay, the temperature should be Kelvin, so you need to compare these two. The company aimed to develop sweeter mixture of sugar. This is high fructose corn syrup. To which one is more? So you just compare the the K constant, and then you can see the difference. And you use the equation that I mentioned, which is this one, and you change just temperature here. This is equilibrium constant at 50 degrees Celsius, which is 0.98, and then 75 is 1.15. So you see that equilibrium is more, so it's produce more products than the lower temperature. As the K increase, the fraction of fructose in equilibrium mixture is increased. Therefore, from the equilibrium point of view, it's more desirable to operate at 75 higher temperature than the lower temperature. Okay, so you use this equation, this one, and you have the 2K, 2 kinetic equilibrium constant, and then you compare the higher one. The higher temperature is desirable for the system. We talk about the yield. True yield, stoichiometric or theoretical yield, is total mass or mole product form divided by reactant used to form that particular product. This is the theoretical yield. But the observed yield is product present divided by of reaction consumed. This is the theoretical one. So different from theoretical one. So sometimes it's different. So you can come back to this slide, and then you see you want to present your observed yield or apparent yield or theoretical yield later on. This is the definition. And for this one, an enzyme catalyze, so from A to B at equilibrium, reaction contain, so at equilibrium the reaction contain 6.3 A and B. Equilibrium constant is concentration of B divided by A. Okay, yield for at the equilibrium. So we see the example. At equilibrium, as I mentioned, so B divided by A is 0.59. Is 0.59. Okay. And total mass conserved in the chemical reaction. So you can notice that the total mass is equal to 10 gram. 10 gram. Okay. And with A at the beginning is only 10 gram. Okay, at the beginning, and at the equilibrium, so it's the ratio is 1:1. So at equilibrium, 3.5 A must have consumed during the reaction. Okay, and it form B. The observed yield is the product produced, which is B, and is from that particular product. So it's from 3.5 gram of A. So the yield of the observed yield is 1. Observed yield, which is this one. Okay, observed yield is this one, B plus mole of A that consumed to produce that product, which is 1. So it's 1:1. Okay, The true yield of A is also 1. Also 1. 1. Also 1. This one, the stoichiometric is 1. Also 1. Gram mole of gram mole. So you can notice from the equation. And the observed yield also 1 gram per gram also. Okay, it's the same. The gross yield is, this is a third term. The gross yield is B divided by A. A total, which is 10.37, which is 1. So you have 3 yields here. Stoichiometric yield, which is this one, 1 to 1. And then the observed yield is 3.7 over 3.7 that produce that one, and the gross yield is 3.7 divided by 10, which is this one. So you have 3 yields here. So you have to look at this definition very, very careful, and then you can do it later on. We will continue on. Total rate is we talk about the total rate. Total rate is the total, mean is, for example, the production rate is 100,000 ton per year, for example. So it's total amount. Volumetric rate, so you divided the rate with volume, for example, like this. This is how you define. So you just have to be more careful on the unit, and then how you can proceed later on. Specific rate, so this is amount of enzyme, for example, amount of enzyme, this one. Quantity, concentration, so this one is amount, this one is concentration. For biological reaction involve enzyme and cell catalyst. Okay, so sometimes it's better to use over the enzyme that you use, or over the cell that you use. So it's more specific on, so just be more careful on the unit that you need to present. And from the experimental data, something like this, so you have time in terms of minute, from 0 to 10 minutes, and then you have oxygen concentration, which is actually is related to the previous one. So your oxygen is decreased over the time, like this. And then you have the different time. This is how you can calculate concentration different by over the time difference. So you have this kind of graph to represent. And this is the way that you present it. It's a delta. Epsilon is a difference of time. For example, this is 2. And this is how you determine the rate of the reaction. So you midpoint to of the slope. And for the kinetic, chemical kinetic in reaction, we have 0 order, we have first order like this, or we will have more than that one. Okay, we talk about the 0 order first. The 0 order mean your rate dCA by dt is Ca over 0, which is 1. Okay, and then you integrate this form to have this one. So you have concentration of A equal to Ca at the beginning minus small k, which is kinetic constant, and T. And if you plot concentration over the t, and then you get the straight line like this. So this is how it look like. So you have the concentration over the time is become linear, so you can assume that is zero order reaction. For this example, Serratia marcescens is cultured in media in the small stir fermenter. Oxygen concentration is measured at this one dry weight. Okay, this is the concentration of oxygen is decreased, so it means that your cell using the concentration. Determine the rate constant. Okay, the small k. If the cell concentration is reduced to from this one to this one, what is the rate concentration? What is the rate constant? First, so we have zero order. Are they okay? We plot. Okay, using the straight line to connect the slope is minus k, and then the k is this one. K0 is this one. Okay, this is K0. Wow, it finished. Okay, we try to find the slope first. Which is minus. Slope like this is minus. The slope is this one, millimolar per min, and this is the slope, and then K0 is this one. K0. Okay, that is too small. The slope is this one. The same cell culture under the same condition. K0 is directly proportional the cell present. Okay, so it's reduced from this to this, so it's getting smaller, getting smaller. So it's reduced from this to this, so it's smaller. You can see 3.5 is lower than 6.7 like this. Okay, the first thing is you look at the graph, and the slope of this one is K0. Okay, that is the zero order reaction, and we continue with the first order. You can see this is the first order, and if you integrate, it's become this one. Ca, concentration of A is Ca0 times e to the power of k1 over t, and if you take all the natural log of the whole one, so you just plot ln A versus t, and your slope is minus k1 now, and your intercept is this one. Ln Ca0 is this one. See, it's this one. The slope is minus k1 now, and this is how the example look like. Soil contaminated with a crude oil is treated with mixture of bacteria and fungi. So you have two things, bacteria and fungi. This is how the petroleum concentration is decreased over the time. This is in terms of day, is quite long. Okay, determine the rate constant, now minus k. So you have this kind of correlation as well. And 16 day, so it's between this one. Your number should be over 588 and lower than 695. Okay, if you are done thing correctly. First, we have this kind of problem. So it's over the time. It look like the zero order, I think. It look like, but it's a semi-log here. So it's semi-log. This one is log, natural log of this one, and this one is the same scale. Okay, it's look like a first order already. Okay, if the first order is look like this, so we have the slope is minus k1, and the intercept is ca0, which is this one. We have this kind of correlation like this, and we plug in, and you can see your concentration is, as I estimate before, it should be over this number but lower than this one. The number is 675 milligram per kilogram. Okay, which is makes sense for this one. And for the biological system, we have different kind of pot. The first one is mechanism maintain kinetics. So you plot this one. This is zero order region, and then V max over 2, which is this one. This one is first order region. So you become from first order to zero order. So it's kind of very complex things like this. So you have the rate, and then V max, Km, and this is your concentration. So it's kind of plot, is mechanism maintain plot. And different enzyme, different sources, different substrate has different Km. So it's summarized on this one. So if you have alpha amylase, alpha amylase, sweet potato substrate, so different kind of Km, which is constant of this one. And see on textbook, so if mechanism maintain is not suitable, so you look for the other things, Langmuir plus, for example. So it kind of fit your data very well, so you can choose one of them. But the most classic one is mechanism maintain plot, and this is how it look like. So this is kinetic of enzyme deactivation. So you have this kind of thing. So what is you want to see? I think we just stop here a bit, and then we continue on the next lecture later on. So I just want to stop you on this one first. See you in the next slides.